when we look at the spatial autocorrelation measures the degree to which similar values occur near each other in space. So if you look at which similar values occur near each other in space, the idea here is that you have, let's say, for example, the values are spreaded like this. We think about a linear space. There are no lateral values. So the values are spreaded like this linearly. And we can have values like 5, 10, 12, 8, 3. When you look at this, you can see that there is some sort of a pattern. There are lower values as compared to the other values like 10, 12, 8. We have 3 and 5, somewhat smaller than them. And of course, we have values like 10, 12, 8 that are comparatively bit larger than them. But statistically, how would they correlate, or how they relate to the entire distribution? We don't know, because we don't know why cannot we think that 8 is a smaller value than 10 and 12, and why do we consider 10 as a large value as well? 12 can be the largest value as well, and 10 can be a much smaller value. So where does this correlation or the distribution variation occurs? So how would we relate that the closer values are related? We don't know. So that is when we use this Moran's index. So this is a global measure. And how do we measure it? We have certain things like N, which indicates the number of spatial objects. So the number of spatial objects. In this case, there are 1, 2, 3, 4, 5. In our case, there are 5 spatial objects. And Wij is coming from the weight matrix. Wij is coming from the weight matrix. I'll come to that in a moment. And yi, y bar, these are the attribute values. So yi indicate the attribute value. The attribute value. So what is the attribute value in this case? These objects are spatial. So you have 1, 2, 3, 4, 5 objects. And for each object, you have an attribute value. Like it can be the price, it can be the height, it can be the temperature, air quality, some sort of a carbon dioxide percentage or something, any value that is belonging to that particular spatial object. So that is the attribute. Yi in that sense is that attribute. So we have y1 as 5 and y2 as 10, y3 as 12, y4 as 8, and y5 as 3. Now we have yi values. And how do we calculate y bar? We calculate y bar by taking the average of values. So the average of values, you have 5 total number of values, and you have the numbers 5, 10, 15, 15, 12, 27, 27, 8, 35, 35 plus 3, 38. So that is 38 divided by 5, which is going to be what? 38 times 2 is 76. Am I correct? 38 times 2 is 76. 76 divided by 10, that is going to be 7.6. Right? So that is y bar. Y bar is equal to 7.6. Right. So we have y bar, we have yi, and then how do we calculate this wij? This is very important in the spatial context, because when you just take yi and y bar, whatever that you have here, those are just related to their attribute values. There is no relationship between the association of the objects. So you have y1 and y2 years, and this can be in a different order as well. And the order, the way they are arranged, is not included in these equations. Y bar doesn't consider how these values are organized. There is no such thing. So that is where we get this Wij. So I talked about Wij last time, about when we talk about the Queen's contiguity and Rook's contiguity, right? In both of these cases, in the case of Queen's contiguity, if you have a value somewhere like this, we have to consider all the values around it for all the 8 directions. So the diagonals and the corners. So this is Queen's contiguity. But if you just consider the Rook's contiguity, that indicates only this direction. So that is Rook's contiguity. Now, how do we put these things in the matrix? So in the last discussion, we talked about how we can develop a matrix, but we didn't necessarily develop a matrix out of it. But I will show you how to do it today. Now, if you just think about the spatial arrangement of this, so let me delete this part to get some space. So we have this linear arrangement. We have n objects. We have n objects, 5 objects. Now, each one of these 5 objects they have their own neighbors. So I told you that if you have n spatial objects, we are looking at a Wij with the dimensions of n to the power 2. So we have n to the power 2 elements here, n by n matrix. So in this n by n matrix, how do we put the values? Closely look at this, what I do. So you have 1, 2, 3, 4, 1, 2, 3, 4, 5 spatial objects. So I am going to develop this n by n matrix. So I'll put 1, 2, 3, 4, 5 here, and 1, 2, 3, 4, 5 here. Now, if you remember the diagonals, now I want you to respond to me. I think you have your chat open. Tell me the diagonals. What will be the weight of the diagonal? For one case, so this is the diagonal, this is the diagonal, 3, 3 is a diagonal, 4, 4 is a diagonal. From what you learn, what will be the value? So this is a binary matrix where you can only have 1 or 0 in our discussion. There can be other values in other cases, but imagine that if they are neighbors, it would be 1. If they are not neighbors, they would be 0. So 1, 1, what will be the value here for this diagonal? Okay, we got an answer. Right, we got another answer. So the answer to this question is a bit tricky. It's not 1. Because if you consider your own self, like 1, the object 1, as its own neighbor, we will have a value that is repeated. And we don't consider that self itself as creating any correlation because it is itself. We just want to see how others contribute to that. So we omit the self correlation. So 2, 2 is 0, 3, 3 is 0, 4, 4 is 0, and 5, 5 is 0. So whenever you refer to weight matrices, the diagonal would be 0. Okay, diagonals would be 0. Now let's look at the others. Now spatial object 1 and spatial object 2. Now tell me what will be the value of 1 and 2 here for this place. What will be the value? 1, 2 case. What is the value? Correct. So for 1, 2 case, that would be 1. Because 2 is a spatial neighbor, it's a neighbor of 1. They are sharing an edge. So they share an edge here, right? They share an edge. So 1, 2 is a neighbor. So it's 1. Now, along the same logic, 1 and 3, they are not neighbors. In our argument, they are not neighbors because they are not sharing an edge. There is no sharing between 1 and 3. So these values would be 0, 0, 0, and 0. Now let's come to spatial object 2. So spatial object 2 is here, and it has a neighbor in 1. So 1 is a neighbor. And when you consider the spatial object 3, it is a neighbor of 2. So it's a neighbor. And others are 0. Spatial object 3 and 1, they are not neighbors. 3 and 2, they are neighbors. And 3 and 4, they are neighbors. And 3 and 5, they are not neighbors. 4 and 1, no. 4, 2, no. 4, 3, yes. And 4, 5, yes. 5, 1, 0, 2, 5, 0, 3, 5, 0, and 4, 5, it is a 1. Now, this is what we call the Wij, or we call the C matrix, actually, the C matrix. We don't go into that discussion here. So just remember, these are Wij values. So this is W11, this is W12, right? So and so. This is basically the weight matrix. Let's keep it like that. Now, once you have it, once you calculate the Y bar, you can calculate all of this using the table. You can create a table and include these values, and you only have to multiply the values that have 1. Others would be 0. So the multiplication would be 0. So you have to only consider about where you have a neighbor. Depending on the rook's contiguity and the queen's contiguity, the values will change, right? So having that in mind, let's go to our hand calculation. I will open a new page for the hand calculation. So I'll drag this. Okay. So we have the question here, question 1 in the spatial handout. And calculation, consider a simple spatial dataset with 5 locations, like I just show you. 5 locations, and the values are here, and the matrix is here. And the spatial weight matrix is based on first order contiguity. Neighbors are adjacent locations on. So we have the calculation. Calculate the global Moran size statistics for the dataset. Now, in this case, we have 12.4 as the mean. So for each location, we calculate yi minus y bar. You can open up an Excel file and just simply calculate the y and y bar if you are doing it by hand on a computer. But in the exam, you will usually get maybe 9 places or something that you can calculate. So you can write it on a table, and yi minus y bar would be there. Just rows, add them up together, and then you get the yi minus y bar. Then you have row standardized weight matrix. So what do you mean by row standardized weight matrix? When we consider their adjacency, in this case, for the 5 spatial objects, for the n by n matrix, now we have 1 for only 1 here. Take the row sum them up row wise. So you have for 2, you have 2 and 2, 2, and 1. Why do we need to row standardize? Now, in the Moran's equation, n divided by sigma Wij would be there. Something like this. So if we keep on doing the math related to this, it will take a lot of computational power and also unnecessary calculations. So in order to normalize this, what we do is we make sure that we get the row normalized value. Row normalized value means we sum them up and then we divide whatever the summation we get, the sum here, we divide the values by the sum. So here it is just 1, but here it is 2. So we divide everything by 2, 0 also we divide by 2, but it is 0. So for other cases also we divide the values by the row sum. And that is what we call the row normalized matrix. So once you row normalize, what happens is this Wij, because they are row normalized, this will be 1, this will be 1, this will be 1, 1, 1. And when you add them together, that will be equal to n. So n divided by n would be 1. Because of that, we can safely omit this part of the equation and calculate the Moran's I. So we row normalize the matrix. So how do we do that? Let me show you. We do the row normalization. And once you do the row normalization, you have the numerator and the denominator. Then the numerator becomes just this, and the denominator becomes this, just the addition of the values. So at the end, you get for location 1, where you have only one value, then you have to multiply by the row normalized value, the weight that you get for the row normalized, that is 0.5 in location number 2. So as you do the math and you add them up together, you have a value. So that is for the numerator 1.2, and calculate the denominator. So denominator would be this. So when you start answering this question, make sure that you do this way. Just write in the yi values, right? And then just put the location or something. 1, 2, 3, 4. Then you have y1. What is the value? Y2, y3, y3. Then you calculate y bar separately. Show the calculation for the y bar and take it yi minus y bar, right? Then in the next part, you have yi minus y bar square. Put them together, and at the end you have the sum of it, right? And that will be helpful. And also put another one to indicate wij, yi minus y bar, and yj minus y bar. That is to indicate the adjacency. So don't get confused by the equation. Basically, this means if you have a 1 somewhere in the weight matrix, then you have to multiply those two values, yi minus y bar. That's all. So you have yi minus y bar here. So what you can do in the exam or when you are answering it by hand, of course, you can sort of put a little knot there, like so which one will be the weight of y1, 2. So if you have 1 here, if you know the neighbor of 1 is 2 or something, then you can put comma 2 in using a pencil or something so that you don't forget. Then you have comma 1, 3 something, and use those values to multiply here. And at the end, you just erase them. So there is no additional things here in the yi minus y bar. So you will get a neat table with the values and the weighted sum. So you have an answer at the end as the denominator and the numerator. Then you get the global Moran sign. And the interpretation, of course, in this case, Moran sign measures global spatial autocorrelation. It ranges from -1 to +1, with 0 indicating random spatial patterns, and it is positive. Right. And I will not talk about the spatial weight matrix problem here because you can understand it. Rook's contiguity and the Queen's contiguity, we have discussed about it. But let's look at the distance-based matrix, which indicates like if you have a space like that spatial object that has some components, you can decide uh, a threshold like 1.5 units, which means if you are considering this one, so this is say spatial object 1, then 1.5 units indicate you have to consider the other part of the point of the value up until 1.15. So you consider this kind of a buffer. For this one also you consider a buffer like that. So like this. So you continue based on the distance that you put, right? And I'm not going to give you such questions in the exam, but you have to understand how it works. That's basically how you get the locations based on the distance. All right, let's look at local Morans index. We have talked about the global Morans. And what is the difference? Now, in the case of global Moran, which we just calculate, global Morans index, we get a single value, just one value. So what do you mean by local Moran? Local Moran means you have to convert all the values into something that is out of a distribution, something that indicates that you are there. Like, for example, like let's say in the global Morans index for a spatial object or set of spatial objects like this, it will lead only one value, just one value. But if you need to understand how each of these values perform, you need to actually calculate a Morans index for each of these values. And how can we do that? Because we only have the equation where you have the weighted sum and divide by the denominator. How do we calculate a local Moran for each of these values? So to do that, we have to first of all calculate the global mean. Global mean means you have attribute values like this, and you have to calculate the y bar, the global mean. And once you calculate the global mean, you can also calculate this thing, S, right? S is this variance, standard deviation. Variance, I forgot there's a C, right? Variance, square root of the variance. And once you do that, we can calculate the Z value by taking Y minus Y bar divided by the standard deviation to convert this values, these mean values, these attribute values into their respective Z score, right? So that is what the process is. How do we convert a value into local Moran? So we calculate the global mean, then the deviation, then this is what we call spatial lag. So what you see here, this sigma here, that is what I just mentioned. And the spatial lag, what do you mean by spatial lag? You are very familiar with it, but you don't understand it in terms of a word. So what is a spatial lag? Now, when you want to take a picture, say a photo, say you want to take a photo, you have different people stacked together, right? I can't draw them properly, so just draw them. So you have different people. So what do? You look at them and you order them based on the height, right? So if you have them in this height arrangement, you can understand how they are spatially spreaded. So spatial lag basically means you first of all draw a mean, you calculate the mean from this, and you draw a line for the mean. And after that, you check the difference. So what is the difference between the value here and the mean? What is the difference of the value here and the mean, here and the mean, here and the mean? So that's what we do, right? So we calculate the spatial lag between the spatial objects. That lag is related to the attribute value, because attribute is the value, spatially they are locked. So what we do in spatial statistics is we consider their spatial part and then we calculate their numerical part. So if you look at this closely, tell me where the spatial part comes in. Look at this equation. Let me put it into different fractions. So this is number 1, this is number 2, and this is number 3. Tell me, where does the spatial component comes into picture? From what part of the equation do you get the spatial part, spatial aspect of the statistics? 1, 2, or 3? Which one? Which one actually uses the spatial relationships, the spatial arrangement of the object in this equation? You have the attribute values. The attribute values can be anything. If you think about the heights of these people, these are the attributes, their height. They can arrange in any way in the space. But when you look at a problem, they are arranged in a particular way. So you consider this arrangement in your calculation. How do you get this? What is the part of the equation here that takes the spatial part of this, spatial arrangement? If I erase this, which part? Send me in the chat which part actually talks about the spatial arrangement of the object in this equation or this formula. Which part? What do you think? In the space, in the arrangement, the location 1, 2, 3, 4, 5, you have them organized. Look at the table. And it says location 1 is a neighbor of 2 and 3. Location 2 is a neighbor of 1, 2, 1, 3, 4. This with 1, 2, 5, 2, 5, 3, 4. Then what is that particular value representing their spatial arrangement here in this equation? It is Wi, Wij. So when you calculate the spatial lag, row standardized weights, each neighbor gets a weight of 0.5. So how do you answer it? You have your yi minus y bar, and you have your neighbor matrix. And let's look at this. No, so 1, 1, 2, 3, 4, 5. Draw your Wij, the weight matrix. Right? Please help me to draw it. Otherwise, you just listen to me and you don't remember what we do here. So help me to fill it. Tell me 1, 1, what is the value? What is the value for 1, 1 here? Zero. And along the same line, all the diagonal values are 0. And the question says 1 is a neighbor of 2, comma 3. So 2 and 3 are neighbors. 4 is not a neighbor, 5 is not a neighbor. Now 2 is a neighbor of 1, 3, and 4. 5 is a 0. And 3 is a neighbor of 1, 2, 5. And 4 is a neighbor of 2 and 5. 5 is a neighbor of 3 and 4. Right? This is how you develop the weight matrix from the data that you are given. And how do we row standardize? Because when you do the calculation, you have to row standardize it, all right? So what is this row sum? First row has 2, second row has a 3, third row has a 3, fourth row has a 2, fifth row has a 2. So how do we do the row standardizing? So this is the row sum. We divide all the weights by the row sum for that particular row. Right? So that is what the row standardized matrix or the weight matrix looks like. Right. Let's go back to our calculation. So we have this row standardized ways with that location force neighbors are 2 and 5. So you can see the row standardized value 0.5 multiplied by their attribute values minus the y bar, and you get the spatial lag for that location. Then the local Moran psi for location 4 is calculated with this equation where you have the standardized value yi minus y bar divided by sigma square. So this particular coefficient in front of it, that gives you that standardization. So you have to calculate sigma as well. You calculate sigma for that value for the distribution, and you convert it to standard normal, and then the spatial lag values are there, and you calculate I4. So likewise, you can calculate I for all of these values. So you can calculate I1, I2, I3, I4, I5. You can calculate values like that. That will give you, now imagine, I'm not drawing this particular scenario, but imagine if you have a matrix like this, then when you calculate the standard or rather the local Moran value, each of these little squares or each of these spatial objects will have a Moran value. This is the value for this I4 in this case, right? So likewise, every spatial object will have a local Moran value using this equation with this. Right. Now, what do we have at the end? We have a set of local Moran values. And then we use this, what we call local index spatial association. Lisa, not Mona Lisa. This is Lisa without Mona. So Lisa, local indexes of spatial association. And how do we calculate it? We calculate all those points, all those I local values, local Moran values, and then, right? Once you calculate all, now look here, okay, yi, not the summation, just yi. So this is the fourth locations y value, attribute value. This is the average of attribute value. This is this standard deviation square of the entire distribution. This is mean for the entire distribution, but this is fourth location's attribute value. So likewise for each location, you will have a different I value. Okay. So once you have them, you can develop a scatter plot. So this Lisa comes into picture with the scatter plot. So we develop a scatter plot for these locations. And from this scatter plot, we can develop, if we develop y equals mx plus c equation here, right? Y equals mx equation, no C, C is 0, and M there is equal to the global Moran. So that is what the math says. So if you develop the scatter plot for the local Moran values and you fit a y equals mx curve, you just draw y equals mx curve, a linear value, and that is global Moran. The slope of that is equal to the global Moran, and others will, when depending on their location on the map, we can say how they are distributed. All right, I will show you with our handout. Now, as you can see, it's difficult to do this by hand. So we have to rely on software to do this. Now, the software that we use for our work, there are two special things that we use. Now, I have shared with you Moran's I Excel, right? I will just show you Moran's I Excel with Excel. This is global Moran, not the local. I have shared this link with you. Hope you can download it. So this is this is global Moran, not the local Moran. So I have created this Excel and I have connected the values in a way that it will give you, depending on the Queen's contiguity, it will give you the global Moran value. So if I change it, for example, you can see the values change and indicating a cluster here in this case. Right? You can also play with it, try to understand how values change. And if you create a very nice distribution of clustering, you can see the global Moran value increasing to a positive value. And if you look at a chessboard kind of a pattern, so let's look at a chessboard pattern. You can see the dispersion of the data. If you look at a chessboard pattern, you can say the dispersion, the negative side of values, right? Look at the values that you can get by changing the spatial pattern. So you can get an intuition about how this thing works. So when you create those kind of clusters or islands, you can see it goes into positive side to indicate clustering or spatial autocorrelation. Clustering in the sense positive values or rather high values contribute to high values. So that is I in that case. Okay. So that is for space, for just for intuition, for you to understand how it works. But how do we do this in a real setting? How do we do this practically? Because you can't do the math all the time with the hand calculations. So how do we do this? We have to rely on software. So the software that we use in this context for this course, I am going to teach you GeoDa and R, and Miss Rojita will teach you QGIS. So you will learn all these three. The GeoDa and R will be used specially for calculations, to understand calculations, how they work. So I will start with the geostatistics in GIS tutorial using GeoDa. Now, I can't see you. I don't know how you interact with me today, but can you send me to the chat? Have you installed GeoDa in your computer? Can you send me a chat message? Have you installed GeoDa in your computer? Have you tried installing or have you? Well, first of all, tell me, have you heard of GeoDa? Have you heard of GeoDa? Have you installed it in your computer? Okay, not installed. Okay. Any other? I think most of you have not installed it. So you can visit this link, GeoDa. Right. This is the place. Let me send it into your chat so you can visit the place. So GeoDa Center GitHub IO. It's an open source software developed by Dr. Luke Aneslin. And before we start learning about it, we have to appreciate what they have done. So Luke Aneslin is a scientist. He is working in the area of spatial analytics in the Arizona State University. Now, he is a very renowned person. He has a lot of books and papers written under his name. And GeoDa is a software developed by his team. And it's a very, very powerful software to teach and also to learn spatial analytics, spatial statistics in general. And we have to appreciate them for their generosity and the efforts that they have put in developing such a good software and making it available for us. So it's a very, very useful thing, and we have to acknowledge them when we start our learning. So we now I think you have GeoDa 1.22 for both macOS and it can be run on Windows, macOS, and Linux, Ubuntu. Just download. Just go to download link and download it. Download for Windows or Mac, depending on your operating system. Now I have installed it for my Windows machine. I can I can show you how the software works, but I can give you 5 minutes wherever you are. If you can, download it to your machine and try to install it. So can you do that? I'll just type in OK. So just put a thumbs up to my OK message and I can wait 5 minutes for you to download and install it in your machine. I'll stay quiet until you download it and install it in your computer. Once you install this GeoDa, we will go to our spatial statistics tutorial. The first one is about the exploratory analysis, which we are familiar with. We'll go to the first part of it. What is spatial data? Spatial data or just spatial data is information that is geographic, that has a geographic component. It is tied to a spatial location on Earth's surface. So remember, this is the important thing that you have to remember about spatial statistics. When you do spatial statistics, you have attributes, the values that change over in the space. They change in the space, but the space does not change. Okay, so the locations are there. An object can have a particular location at a given time, and that object will have a different location in another time. So it has moved from location 1 to location 2, but location 1 and location 2, they are the same on the map. So by statistics, when we say we do statistics, what we do is we try to come up with statistical interpretations about the values in the space, so attribute values in the space. And if you are looking at the geometric data like the shape or the distance or the length of a location, of length of a line or an area of a polygon, we have geometric interpretations, yes, but the spatial attributes, the spatial part of the statistics will have its own complexity as well as consistency. So you do not combine these two And when you say spatial statistics, you don't, in your statistics, you don't just take the mean of coordinates like out of nowhere, or you don't just add the coordinates up without any idea of what is that in the context of space and how the objects are dispersed in the space. So we have to consider their spatial aspect as well. In simple terms, what I mean is, if I explain it a bit cleaner than that. So if you have spatially distributed or spatial values like this, for example, so this can be 6, 10, 15, and 3. So in other words, this can be maybe a river part of a river, for example. This may be a river, and this may be a land lot, land part, maybe vegetation or something. Because of their spatial nature, their property, you may have a value of 6 for something, some attribute, a value of 3 for some attribute, a value of 10 for some attribute, and value of 15 for some attribute. Same attribute, because of their spatial nature, you have different values. When you treat them in statistical terms, right? When you treat them statistically, you only look at these values, right? Getting the average, getting the mean, getting the standard deviation, whatever. But when you do spatial statistics, their association, where do they lie in space? And what are their neighbors? And what sort of things dictate their spatial value? That is important, and we consider them. You can't just blindly take these values and then, okay, right, I don't care where the 6 is. I just write 6 is here, and I don't know, 5 is here, and 3 is here, and 10 is here. It's the same set of values in terms of the numbers. 6 is the same, 5 is the same, 10 is the same. It's the same, but their spatial arrangement is different. Like when we deal with permutations, NPR. In the case of permutations, if you have ABCD and ACBD, these are two different permutations. This is different to this, right? This is different than this. So these are two different permutations. If you think about your passkey or your password may be something, but you have to give that order. Otherwise, it's not considered as your correct password. So NPR matters. In the spatial context, this is also the same. You have to consider their spatial arrangement when you do your calculations. Because of that, this thing becomes also very complicated and very interesting at the same time, because you can't have a river and a land lot uh, in multiple different combinations. You have to have that in a particular defined code combination or permutation. Right. So we have shape files in the software .shp. It's a proprietary term used by Esri. So it's SHP shape files for the shapes, and DBF for the database files, SHX for the spatial indexing, PRJ for the project files. So we need all these four type of files in order to do a spatial calculation or a spatial analysis, because these are taken for our buffer analysis, for our correlation analysis, or whatever we do. We need this. And exploratory spatial data analysis, or ISDA, is the exploratory data analysis part we do with spatial data. So we have an idea about exploratory data analysis, right? We take the mean, we take the standard deviation, we do all these things, but we take spatial context into it, and then we can call it ISDA, or exploratory spatial data analysis. Let's start with our first thing. I have put the links. These are publicly available data, so you can click on them and download them. I will go through the handout one by one. So we have installed it, and we need the data. Just click on this, and it will be downloaded to your machine as a zip file. I have it downloaded. This is Columbus dataset, and extract the data zip file. So you get this Columbus folder inside Columbus, you will have this. So you have .shp file, GeoJSON files, geo packages, GPKGs for geo packages, HTML, KML for the Google Earth, then a lot of different types of files, but we just need SHP, SHX, and DBF and PRJ file for our work, right? So that is there. I have just extracted the folder. Then first we will open, we are working with our GeoDa. So let me open GeoDa and explain the components of GeoDa. So GeoDa looks like this, a very colorful icon. And once you open it, and this is the graphical user part where you can see the map. When you connect the data source, you will be connecting it to this. And this part is the part that has those components. Without connecting data, it doesn't allow you to move. So I will just connect the data as the handout says. So I have to connect my data source. I am lazy to do all these things. So I'll just take it to my folder and I just drag my .shp file to this, drag the shp file to this and drop it. Now you can see the data set. Minimize this. So this is the map. And on the top, I will explain the ribbon. So this ribbon contains the type of analysis that you can do with GeoDa. You have obviously save as, and project, etc. And then edit, time, and category. You have tools for weights manager and shape. Weights manager is that spatial weights matrix. We'll talk about it. And then you have table for calculating various spatial calculations, and you have exploring histograms and other things, clusters, principal component analysis, k-means clustering, hierarchical clustering, dbscan, the things that you learn, k-means clustering. And then you have univariate Moran, bivariate Moran, which we didn't discuss. Univariate Moran is what we discussed. Univariate local Morans is the other one that we just discussed today. And local G and G star. Then you have other types of Lisa, univariate quantile Lisa. You can learn about these things as you work. Then regression analysis, then options are also there. And let's go ahead with our handout as we. So we will need to load it, right? We drag the Columbus SHP and open a map of the Columbus neighborhoods will appear. Step number 3, 1.4.3. Create a choropleth map. So what is a choropleth map? A choropleth map is a color map which indicates the color as the intensity, like the population density, the crime rate, whatever the value that you have in that spatial extent, you assign a color to that. So that's a choropleth map. It's a color. Right click on the map and select change current map type. So we are here, right click. So this is the map, right click and change the current map, right? And the instruction, what is it? Number 2, choose a variable to map, for example, crime. A dialog will appear for map classification. Number of categories, choose 5. For the classification method, select quantile. So I'll go with the quantile map, right click, go to quantile map with 5 classes. So this is what you have to do. Change current map type, quantile 5. And the variable is the crime, right? Crime. So crime rate. That's the variable. And say okay. Now you can see based on the crime rate or the density of the crimes, it has divided the entire map into 5 classes. 1, 2, 3, 4, 5. 5 different classes. You can see different colors for that. Right. So we have that. The map will now be colored to show the spatial distribution of crime. That is 1.4.3, step number 5. Let's go and do the basic descriptive statistics. With the map window active, go to explore. So can we see explore here on the map? No, we can go to this ribbon, explore and histogram. Explore histogram and select the crime. So crime is the variable. Select crime, say OK. And now you can see a very nice histogram. So have you done this up to now? Those who have downloaded and used the data set, have you come this far? So I am asking yes. So if you have done this so far, just put a thumbs up, please. So I can wait until others also do that. Those who have created the quantile map and the histogram, just put a thumbs up to my yes message. Just do it so I know you are following. Okay. At least one. Anyone who's doing it, just put a thumbs up to my yes message. Okay, if you can see this quantile map and the histogram in your computer. No one. All right. Okay, at least one. One is there. One thumbs up. Right. So now you can see the quantile map, 5 classes, because we chose 5 classes. And look what happens. If you hover around the histogram and click on one of these classes, you can see how the map change. Like, like with any BI software like Power BI, this is a very dynamic visualization. You can click on them, and based on that, you can see how the map changes. And also, if you select an area, a particular area, you can draw a little square like this. And based on that, you can see the histogram changing. And if you press shift button on your keyboard, or on your Mac keyboard also shift, just click on the colors and you can nicely see how they change. So see the colors, the highest crime rate, for example, if you are interested in these colors, this particular area, I can just very easily click on the color of the class and you can see how they, right? And so that is the quantile map and how you interact with the histogram, right? So you can, it's a dynamic way. Now let's go to the second one, dynamic linking. I have done it. Click on bar on the histogram and it changes. So this dynamic linking is core feature of Hista in GeoDa, allowing you to instantly see the graphic location of statistical patterns. Right. So the R implementation, okay, this R code works because I have coded it. So this will be one of your lab assignments where you use R to do it. So I'm not going to do it here in this class. Okay. So creating a choropleth map, all these things work, all these codes work, and I have done it. So there is no issue with the code. You have to run it and see how it works. I will give you this as a lab exercise with some more R codes. So just leave it at this instance. And then let's look at spatial autocorrelation with global morans, how to get global morans index from our data set. So how do we get it? Because we need spatial weights metrics as well. And how do we set it up? I will explain how we do it. And this will be also given as a group work for your teams. So at least one person in the group just learn it well. So Moran scatter plot, how do we develop a Moran scatter plot and a weight matrix here? So you have Columbus crime data set, the same Columbus data set. So we have already opened it. This is it. And now we are going to develop the weights manager. So what is weights manager? If you go to this one, the ribbon at the top, right? There is an option called Tools Weights Manager. Tools Weights Manager. Click on this and it allows you to create weights or load weights. Create or load weights, right? So in order to create or load weights, we need to know what are the indexes or what are the spatial numbers. So like we did in our calculations, what is this particular block here, for example? What is this? What is this? What is this? So how do they relate in space? So to do that, we first of all, let's look at the attribute table. Click on this table icon here, and you can see this attribute table like this. And there you have poly ID, that is polygon ID. And that ID is what we will be using in our case. So Columbus there are other values as well. If they are there, that's all right. But poly ID is the ID that gives us which one is the neighbor. Now, for example, if I click on this, as you can see, and it also shows us which one is the neighbor. See, poly ID and the neighbor. If you click on the attribute table, you can see ID and the neighbor, right? There are other neighbors associated with that. So we don't need this neighbor column right now here, but we will use poly ID as our identification of the polygon. Okay, that's what identifies our polygon. So that in mind, let me close it and also close this entire thing. Let's go to our weights manager. And when we create it, it will ask us what is that variable? What is that variable for the polygon ID? So I will just select poly ID. Poly ID with Queen's contiguity. Order of contiguity is 1, right? And then create. So I will just use Columbus Queen. I have developed this weight matrix before. I'll just use 2026 here and save it. Right? It is created and it is loaded. Columbus is loaded. Then we close this. And look at this. You can see the number of spatial objects, 49, and their order, connectivity, ID variable, polygon ID, and the number of neighbors, mean neighborhood, etc., etc. You can also look at the connectivity map. This is very, very nice, very cool. See, when you click on connectivity map, you will get to see the neighbors, isn't it? Nice. It's really cool, right? You can look at the neighbors. Carefully look at the neighbors as well. So this is very useful Very nice tool to see the neighbors, and accordingly you can see the crime rate changing. For example, if you look at the neighbor with this, and you can see their connectivity. See, it's very nice. Very, very nice. So that's connectivity map. Also, histogram is there, how number of neighbors change over the time, or sorry, over the space, and the connectivity graph. This is also very powerful because it shows you how each polygon is connected. Say we are dealing with crime rates, right? How the crimes are connected. Like let's say we are dealing with drug problem, for example. Drugs may come to this particular county or this area use through all the other spaces with the queen contiguity. See, we can see the connectivity. It's very, very useful. Right. That being said, so we have created our Columbus queen contiguity weights matrix, and then just load it. We just keep it and just click on it and then close it. That's all. It's loaded, already loaded. So we go to we can go to tools either. So we can just go ahead and with the options, rather space. What are we doing here? We created it. Now we'll go with Moran's index. Space univariate Moran's I for the global measure. So we are on the map. We'll go to the space univariate Moran's I. That is the global Moran's I index. Click. And the variable, I told you, space is space. On the space, you have different variables. We are looking at the crime. So I'll click on crime. And the weights is the Columbus Queen 2026, which we just created. Click on crime. Say OK. And now you get this. This is Moran's scatter plot. And notice that the x-axis is not the x-axis that we are used to. It is from negative 2.6 and there's a 0, and this is the continuation. Here it's from negative 2.6, it goes up as well. So 0 is somewhere at the center here. And based on the Moran's index, let me show you a very cool thing. So this is the Moran's scatter plot. And when you look at these points in space, you can select them. And this is high cluster. So now you can see how high values are associated with high values. And you can also, this is the low cluster. You can see how low values are associated with the low values. And this is high-low, how high and low are associated, see? And here you can see low-high, right? So with that, we can do this spatial analysis very cleanly to understand how they are correlated or how they are contributing. So here, Moran's index is 0.5, which indicates positive spatial autocorrelation, where the positive ones are contributing to positive ones. So it's 0.5. And we can also randomize this. So what do you mean by randomizing this? Randomizing means it's NPR. Let me explain it to you. Now, I told you early on when I start this part of the lecture that the space is important, right? So what do you mean by permutations that in this handout? So I told you this the spatial arrangement is important. Say 5, 10, 11, 17, 30, 20, 8, 6, 3. I told you these values are arranged in space. So the spatial arrangement is important. That needs to be fixed in our analysis. However, when we do this calculation for the Moran's index, so the global Moran and Moran scatter plot, we need to know whether this arrangement is random or not, whether these points are randomly arranged or not, do they have a particular special meaning in the space. So to do that, what we do is we swap them or we interchange them, we change their position. So we do some permutations. We put 5 to this place, 30 to this place, 70 to this place, 6 to this place, 3 to this place, 10 to this place. Likewise, we change the allocation. So that is what permutation means. We permutate the spatial things, spatial objects, and see with different arrangements what will be our answer. So that's what it says under finding the significance in the Moran scatterplot window. Click on randomization tab, set the number of permutations. So this is our Moran scatterplot. Right click, randomization. On the Moran scatterplot, right click, randomization. So this is the number of permutations. So you have 49 objects, right? 49 spatial objects. You can imagine the calculations. 49 permutations with the neighbors. Imagine how we can organize them in space. So we can go to 999 permutations or above. So I'll just go ahead with I'll go ahead with 999 permutations. And now you can see with the permutations, what is the value that you got for your value was 0.5 something. Expected Moran is also given, and the average of the permutation values are also given in this line. So your one is significantly towards the right hand side, which indicates there is a positive autocorrelation. So see, whenever we play this, you can find how the permutation works, and your Morans are here in this phase. So it's a very, very useful tool, and you can easily understand, you can run it. So you can keep on running from different combinations. You get Moran psi calculated, and that will show you how your distribution is. That's a very useful tool. And pseudo p-value will be displayed. This tells you the probability of getting a Moran's value as extreme as the one you observed if there were no spatial pattern. So randomized calculation. So if it is random, how likely are you to get the Moran psi that you are getting? If the spatial pattern is random, how likely are you to get that Moran's index that you have just got? So it's very, if it is very low, it means there is some sort of a pattern. So that's what it means, right? So let's go down a bit towards our LISA, local indicators of spatial. So you have high, hotspot, low, cold spot, and high, low, high. So these are LISA, and you have Chicago Health. Since I haven't, I will be interacting with you in another lecture, so I will allow you to do it. Now in this data set, cancer B data is not available because I think after the racial issues with the Black Lives Matters something, this particular, because cancer B is the cancer of black people. It is not there in the new data set. So I can open this up. So if you download this in the com area data, let me close it to show you what I mean. So if I open this com area data, HP, if you open it, you will not be able to see cancer B data, because if you open this table, cancer B data is no longer there. Look at the attributes, the column names, the cancer B data is no longer there. I think after some issues with the racial matters, I think that the things were removed. You can, of course, use breast cancer or any other value that you like and test it out. So follow the same thing, but with a different variable, not cancer B. For example, since I have the weight matrix also, let me quickly show you. I'll go to the space and univariate Moran. Could not find the weights manager, so I go to weights manager and load the weights. I have com area, Q weights, Queen's contiguity, and I will just do univariate Moran with the breast cancer. Yes, breast cancer, all breast cancer. Say okay. and you can see the association. So it's a very powerful tool, to be honest. Like, you can use it, you can do a lot of things with it and find out how they cancel. So if you go to bivariate Moran, for example, I'll go to bivariate Moran. This is not related to your lecture, but I'll show you bivariate Moran. So you can use breast cancer and say breast cancer as X variable, and as Y variable, let's say something else. I don't know. Like, let's look at fertility rate, for example. Breast cancer and the fertility rate. Birth rate, breast cancer and the birth rate, how they are spatially related. So we are using bivariate Moran, and now you can see if they are where they are spatially related. The high, low. This is high. This is low, high. This is high, low. Sorry, this is low, high, and this is low, low. Sorry, this is low, low. This is low, high, and this is high, low. So based on the quadrant that you are in, you can see how they are distributed. So it's bivariate Moran. So you can think of how you can use it. So just go through this, and G-star statistics is also there. For these three spatial autocorrelation related activities, I will give you a lab exercise in R and GeoDa both, for one question with GeoDa activity and one question with R. So you need to see how you can replicate it in your computer, right? So you can use the recording that we have here, and you can also, by all means, please explore yourself. You have tons of very interesting details and tutorials and materials that you can use. So please go ahead and explore them and try to get hold of GeoDa and R. All right.